Okay, so today we're going to look at lesson 11.1. That's actually supposed to be 11. Let me put that in there. 11.1. And we're going to cover what is light. Okay, this is the first lesson for our optics unit, and we will have a little bit of homework for this after the lesson is complete. So if you can pay attention, and then we'll move along here. Okay, so some simple facts about light. So one, light is from the sun, and it is responsible for all life on Earth. It heats up the Earth's surface. We wouldn't be able to be here because the Earth is in a zone called the habitable zone where light provides that heat that is appropriate for us to survive and for animals and plants to survive. Also, if it wasn't for light, there would be no ecosystems. There would be no food chain. The whole food chain would collapse because photosynthesis wouldn't occur. So light does provide us with a lot of different um, benefits, and it allows us to be here on Earth. Light travels at a very high speed at 3.0 times 10 to the 8th meters per second, which is equivalent to 1.08 billion kilometers per hour. Okay, so if a light beam were to travel around the world in outer space, and I say outer space because that's the speed of light in a vacuum, and 3.0 times 10 to the 8 meters per second is the speed of light in outer space. Okay, it would actually take light 1/7 of a second to travel around the whole entire globe. Okay, or it can travel around the whole entire globe 7.5 times in 1 second. Okay, so it's very, very fast. The third little interesting fact is light travels in a straight line. Okay, and this is evident through shadows. Light doesn't bend. It's not like it's coming down and it's like, oh, I have an object here. I'm going to go here. Okay, light travels in a straight line, and that's why we have shadows, and that's why shadows are part of our everyday lives. Um, now, we do everything that we can in order to get rid of shadows, whether we put lights there, or we put lights certain areas, certain distances apart in order to get rid of a lot of those shadows, say when we're reading or something like that. Okay, so light does travel in a straight line, and that is proof, and we can prove that through shadows. Okay, some couple of vocabulary words that we're going to talk about and will be talked about heavily throughout this unit is a medium. So when we say a medium, okay, it is any physical substance through which energy can be transferred. Okay, for example, a metal spoon is a physical substance where, if you remember, heat can travel through that medium of a metal spoon by conduction. Hot air travels through air by convection, so air would be a medium. Water could be a medium, or glass can even be a medium. Okay, and we'll talk about that a little bit more in detail as we move through. But just know a medium is any physical substance through which energy can be transferred. Again, water, air, um, metal could potentially be a medium for heat. Okay, what's interesting about this is that light is the only form of energy that can travel without a medium. Okay, because it travels through radiation. Heat, you need some sort of medium to make heat move from one area to another area. Even sound, okay, sound needs particles in the air in order for it to travel, okay, because it vibrates those particles and allows us to hear specific sounds. So light doesn't actually need that. It actually transferred through radiation, through wavelengths. Okay. So those movies where you see huge explosions in outer space and you can see and you can hear the big explosion. Well, you might not be able to hear a huge explosion in outer space because there's not a lot of particles in outer space for that sound to vibrate off of. Okay, the sound waves hit our eardrums and it vibrates that sound into our brain, into our eardrums, and then our brain perceives that as sound. Okay, light does not need those. It can be transferred in space or in a vacuum where there is no medium. Okay, light behaves like a special kind of wave called an electromagnetic wave. And electromagnetic waves are like water waves in that they transfer, or like water waves or sound waves in that they transfer energy from one area to another area. Okay, but again, light waves do not necessarily need a medium or need something in order to travel. They can travel through radiation from one area to another area, from the sun, say, to Earth. Okay, Again, it is just a transfer of energy from one area to another area. Okay, this radiation can be looked at as a wavelength. Okay, this would be an example of a wavelength. You have your crest right here, you have your trough right here, and the distance between your crest and your trough, or your crest and from crest to crest or trough to trough, would be considered the wavelength distance. Okay, and the smaller that distance, the more energy that that wavelength has. Okay, so if we spread these waves out farther, okay, if we spread these out farther, there's less energy. And we're going to look at the electromagnetic spectrum in a second to show you the different types of electromagnetic waves. But the larger you spread these waves out, the less energy. And you can think of that as even, oh yeah, we'll talk about it in a second. Okay, the electromagnetic waves are a lot more complicated than say water waves or sound waves, in that it is where the electric field and the magnetic field come together. And you can see from this diagram, they come together perpendicularly and they travel in that one direction, in that one, in this one direction in a straight line. Okay, you have your wavelength is crest to crest, or you could look at it, your wavelength from trough to trough. And again, the shorter that wavelength, the more energy, the more energy that that wavelength carries. Okay, so this is an image of the electromagnetic spectrum. We have radio waves all the way over here. And radio waves are what we communicate through, like from NASA to the International Space Station. That's why we can communicate. We do not communicate to the International Space Station with, say, sound waves, mainly because sound waves, again, don't carry through outer space very well, so we use radio waves. Okay, the electromagnetic diagram shows the range of electromagnetic waves in order of wavelength or energy. Okay, you remember how I said the shorter the wavelength, the more energy there is? Well, this is an example of it, right? Radio waves are not, they do not have a high frequency, they do not have a high energy, so they're really long and large. And as we move from left to right, we see that these wavelengths get shorter and shorter and shorter, okay, until we get to gamma rays. Okay, gamma rays are photons that are released by radioactive isotopes, or decaying radioactive isotopes. We have X-rays here. This is when you go to the hospital and you take a picture of your bones. A really great job, actually, X-ray tech, if you ever if you want to do something like that. Then you have ultraviolet light. That's the ultraviolet light, UVA, UVB, that get released and cause us to burn. And then we have this really small portion right here, okay, and this is called visible light. Okay, visible light comes to us from the sun as a form of white light, and white light bounces off of certain mediums and causes us to see all the different colors of the spectrum. If you can see in the spectrum, you have like red, orange, yellow, green, blue, and violet, blue, violet, purple. This is the strength of those wavelengths. Okay, as you move from left to right, you're going to get stronger and stronger wavelengths. Okay, then you have infrared, microwaves, as well as radio waves. Infrared would be like waves released by a fire, microwaves released by your microwave cooking potentially, and then radio waves by a radio. You do need to memorize this in order, so this is a little mnemonic that you can remember. Raging Martians invaded Venus using X-ray guns. Radio, microwaves, infrared, visible light, ultraviolet light, X-rays, and gamma rays. Okay, and this is just another way to show you the wavelengths here. Okay, when we get all the way to gamma ray, these are the most energy-filled electromagnetic waves, and they are the size of, say, subatomic particles. Okay, yeah. So the shorter the wavelength, I want you to get out of this, the shorter the wavelength, the higher the energy. You can see your textbook at page 466, and you can see the common uses of each category of electromagnetic waves. What we're going to focus on here, and you're going to actually, so sorry, for your quiz, you're going to actually need to know some uses for these different types of waves, wavelengths. So make sure to take a look at that, and we can discuss that in class as well. Okay, but for this unit, we're really going to be focusing on the visible light. Okay, and this is the visible spectrum. These are the range of wavelengths that are detectable by the human eye, and that's just the human eye. Okay, some different species or some different animals can detect different wavelengths that we potentially cannot detect. I've read that dogs can't see certain types of colors. That's because their eyes cannot detect the wavelength at those colors. Okay, but they can see other colors. So, different species or different animals may not detect the exact same visible light, or they might not have the exact same ability to see the visible spectrum that we can. Okay, a visible spectrum can be used to separate white light into 7 different colors. Again, the sun releases white light. The sun releases all the different types of visible light that we potentially can, but we can't see it as it comes down to Earth. We can't see this white light as it comes down to Earth. It has to bounce off of something. And I'm sure a lot of you have seen this little prism. Okay, this prism bends white light. So this is your white light coming in, and it bends the white light and slows down the wavelengths as the waves interact with the prism. Okay, and it slows down these wavelengths to certain to specific wavelengths that allow us to see these specific colors. And like I said before, you can see your slowest color would be your red light, and your fastest, your least energy would be your red, and then your strongest energy would be your violet. Okay, so again, these are white light comes down from the sun and it bounces off, and that's how we see color. Okay, is that certain mediums interact with the white light in a specific way that allow us that causes the light to slow down and allows us to see the specific colors. Okay, so that brings us to the end of this lesson. Your homework for today or for this period is to read pages 469, read pages 463 to 468 and complete homework on 469, questions 1 to 10. Okay, in our lesson, we'll talk a little bit more about this, but this is what I want you to work on as of right now. Okay, guys, we will chat later.